previous lecture we were discussing about the generalized way of writing the Newton's law of viscosity, and we eventually wrote tau ij is equal to So, we will discuss about the contextual relevance of normal stress and shear stress from here, but before that let us see whether we could reduce our number of equations and number of unknowns. So, previously the equations were how many? Unknowns were how many? There were 10 unknowns. Now, how many unknowns are there? Rho is an unknown, p is an unknown, and the 3 velocity components. So, total 5 unknowns. Number of equations still those 4, right. So, it may close the system only if either rho is constant or rho is specified. We will see if rho is not a constant or if rho is not specified what to do, but assuming that this actually is leading us towards a closure, that is we are reducing the gap between the number of equations and number of unknowns, let us evaluate this derivative to complete the description of the equation of motion. So, that was there in the right hand side of the Navier's equation if you remember. So, this will become right the first term, delta ij is 1 if j is equal to I. So, this will become xi derivative, okay. Then okay, and then remember mu is not a function of position, right, because it is a homogeneous fluid. Because this mu is a constant, you could as well take it inside the derivative or outside the derivative, it does not make much of a difference. So, sometimes you know this is the way in which we write, because it is not a function of position, this will not matter. And the final term, because it is a continuous partial derivative, you can swap this xi and xj. So, because this is a dummy index, see now j has become dummy because j is a repeated index that is summed up. So, this you can call it del u k del x k. So, these two terms you can combine together and write clearly. For incompressible flow this term does not matter. So, for incompressible flow the parameter lambda is irrelevant, it is not at all important what it is, but for compressible flow this term is not 0 and therefore there is a chance that it has a spatial derivative, and therefore one needs to recognize the relationship between lambda and mu. So, to do that let us write tau 11. So, tau 11 is minus p plus lambda del u k del x k plus 2 mu del u 1 del x 1. See a very important thing, this is again a misconcept in students. The misconcept is that only possible normal stress is due to pressure. This is a misconcept. There can be a normal stress due to viscous effect also. See this term, this is called as viscous normal stress. So, this term is there because of the linear deformation and coupled with viscosity that is giving rise to a normal stress. So, viscosity does not just give rise to shear stress, shear stress is due to viscosity, but viscosity is not just giving rise to shear stress, it can also give rise to normal stress. This is something which is not explicitly taught to students, but I think this must be explicitly told. And normal stress could be due to volumetric deformation, that is quite clear, that if there is a volume element which is stretching or contracting there should be a normal stress. Similarly, tau 22 So, if you add all these effects, and make an average, this is called as minus of mechanical pressure by definition. What is PM is mechanical pressure. Mechanical pressure is just the arithmetic average of the normal components of the stress with a minus sign, because normal components of the stress are tensile if they are positive, but pressure is by definition compressive if it is positive. So, this is average normal stress, this is defined as mechanical pressure, and this P is defined as thermodynamic pressure. What is the difference? The thermodynamic pressure will have all possible degrees of freedom embedded within it of molecules, rotational, translational, vibrational, etc. And the mechanical pressure is a manifestation of all these eventually converted into translational degrees of freedom. So, that is the basic difference. So, this is equal to, now if you sum this 3 and divide by 3, this will be minus P plus 3 lambda by 3 plus 2 mu by 3 into del u1 del x1 plus del u2 del x2 plus del u3 del x3, that is also del uk del xk. So, plus lambda plus 2 mu by 3 del uk del xk. Now, the very important question, will the mechanical pressure be equal to thermodynamic pressure? In one case obviously yes, when it is incompressible flow, but when it is compressible flow there is nothing fundamental which tells us that the mechanical pressure must be equal to thermodynamic pressure until and unless we hypothesize it, and the hypothesization can be through some argument. See, normally the fluids relax to a state of local equilibrium very fast. So, if you impose a force on the fluid will relax to its new equilibrium state as a consequence of that force very rapidly. So, all the degrees of freedom will instantaneously be converted to the translational degrees of freedom, and that is how it comes to an equilibrium everywhere. So, this means that the mechanical pressure will become same as thermodynamic pressure. However, if you impose such a rapid disturbance to the fluid that before coming to an equilibrium state a new disturbance has come onto the fluid. For an example, let us say that there is a bubble which is rapidly expanding and contracting like this. Now, before the bubble comes to a new equilibrium state, another excitation force has come, so it starts expanding, contracting. In this way, the time scale of imposition of the disturbance, if it is faster or shorter than the relaxation time of the fluid itself, then the fluid will not be able to relax to an equilibrium state, and then it will not be able to achieve the equality between mechanical and thermodynamic pressure. Under that circumstances, mechanical pressure will not be equal to thermodynamic pressure. So, mechanical pressure equal to thermodynamic pressure this is an hypothesis which for most practical processes, but the time scale is not that rapid, this will be satisfied, and this is leading to something which is called as Stokes hypothesis. It is called as a hypothesis because it cannot be proved, just by arguments it can be justified for most of the cases. So, if that be the case, then the obvious conclusion is lambda plus 2 mu by 3 is equal to 0, that means lambda is equal to minus 2/3 of mu. This is the so called Stokes hypothesis, and the fluid that obeys this is called as a Stokesian fluid. So, the understanding is that for a Stokesian fluid, see, first we had Cij Kl 81 independent constants. Now, we have brought down the number of constants. So, from 81 to first 3 constants for homogeneous and isotropic fluid, and then to 2 constants by exploiting the symmetry of the stress tensor, and now for a Stokesian fluid only to 1 constant, which is the viscosity of the fluid. So, that is, you see the how strong and pivotal role the viscosity plays. The other interesting thing is that because mu is positive, lambda is negative. So, what is the physical implication of lambda negative? So, if you have this as positive, then the corresponding stress is negative, corresponding part of the stress. Why? Because lambda is negative, those negative into positive will make that component of this negative. So, the physical implication is that if you have a fluid element which is already expanding, then the incremental stress to stretch it further is negative. If it is already expanding or stretching. That is the physical implication of negative lambda. So now we are in a position to write the equation of motion by using the last step in the board, the last line in the board, which I will not erase, but I will erase most of the remaining part. So this now will become lambda is equal to minus 2/3 mu plus mu will become mu by 3. So rho this mu you can clearly bring out. So now let us look into the number of equations, number of unknowns, etc., and then we will see also the vector form. Maybe let us first see the vector form and then we will look into the number of equations, number of unknowns, etc. So now this equation, number of equations, how many? Or look, let us first see the vector form. So this is the ith component. So you can write I equal to 1, one such equation, I equal to 2, so I equal to 1, I equal to 2 and I equal to 3, 3 such equations. Multiply the I equal to 1 with unit vector along x1, I equal to 2 with unit vector along x2 and I equal to 3 with unit vector along x3 and vectorially add that. So then what it will become? So what will be this? Right? So this is the Navier-Stokes equation, so called the celebrated Navier-Stokes equation in vector form. Anybody doing a course in fluid mechanics is and not going through this Navier-Stokes equation, the course remains incomplete. What I intend to say is that in junior classes, if we at all talk about the Navier-Stokes equation, we straight away state the equation, but it is very important to go through the rigorous exercise that I have passed through, starting from the Reynolds transport theorem momentum conservation to the Navier-Stokes equation. So what are the assumptions? The first assumption, keep in mind that there is no body couple, the Navier equation, and then homogeneous, isotropic, Newtonian and Stokesian fluid. So these 5 major assumptions, and any other assumption can lead to an additional body force which can be dumped here. Okay. Now let us look into the balance of the number of equations and number of unknowns. So you have 3 such momentum equations and 1 continuity. So 4 equations. Unknowns, now pressure has come as an unknown, density is there as an unknown, and U1, U2, U3. The advantage with this vector form is that now you can use polar coordinate or whatever coordinate to describe this, whereas still you use the Cartesian index, that is true only for Cartesian coordinate. So these indicate you have 4 equations and 5 unknowns, right. So this is EQ, this is unknown. So how do you patch it up? So one clear possibility is rho is constant or rho is given. Then continuity and Navier-Stokes, they form a closed equation. If rho is not given, then rho can be a function of what? Rho can be a function of pressure and temperature. For a simple compressible substance, rho is a function of 2 independent variables, say pressure and temperature, until and unless it is changing its phase. So if rho is a function of pressure and temperature, then that is what is the equation of state essentially, like P by rho equal to RT is the ideal gas equation of state. Similarly, for any other substance you have rho as a function of P and T, this is equation of state. For ideal gas, P by rho is RT. For non-ideal substance it could be something else. So if T is constant or a given, then this equation will give another relationship between P and rho. So then you will have 5 equations and 5 unknowns. But if T is not constant, then you have a governing equation that describes the variation of temperature, and that is nothing but the energy equation which is studied in heat transfer. So as a teacher of fluid mechanics, if you are introducing your students to heat transfer, typically convection heat transfer, you can start from here and say that where is the perspective where fluid mechanics and heat transfer are mathematically connected. Now finally, as a final remark, what are the challenges in solving this equation? See, in the industrial world, in the real scenario, solving Navier-Stokes equation is a big thing, and the challenges of solving the Navier-Stokes equation are as follows. First of all, look into this term, this is a non-linear term. So the Navier-Stokes equation along with the continuity equation represents a coupled system of non-linear partial differential equations, which in the most general sense does not have any analytical solution. In certain special cases it may have analytical solution, and that we will discuss in the next lecture. The other issue is that there is a pressure as a variable, but there is no separate governing equation that explicitly governs the variation of pressure. So only way is that either you eliminate this pressure in some way or the other, or you link this pressure with the continuity equation. That is done using some computational techniques in the computational fluid dynamics paradigm. So CFD is so important in research and in practical applications because the Navier-Stokes equation does not have analytical solution. In general not, in special cases yes. So the non-linearity, the coupled nature and the peculiar behavior of pressure, that is there is no separate governing equation for pressure, but pressure has appeared as a variable. That makes the Navier-Stokes equation so unique and computational fluid dynamics techniques so important. The final remark that I want to make in this particular lecture is a little bit of pedagogical note. Earlier when the fluid mechanics courses were designed differently, fluid statics was used as the first chapter. Now presently in advanced courses what is done is that the fluid statics chapter is sometimes not treated separately. The reason is like this. So if you have this equation and you set all the velocity terms to 0, you are left with this equation, right. This is just an equation for fluid statics, with gravity being the only body force. This will be the governing equation that relates the pressure gradient with gravity. So fluid statics can be recovered as a special case of fluid dynamics, and therefore because every course has limited time, it may not be a good idea to have a separate elaborate discussion on fluid statics, because it may eat up a significant amount of time for teaching advanced materials in the course. This is what is my viewpoint. Different people may have different ideas. Possibly for a very junior level course it is good to introduce fluid statics at the beginning, but not at an advanced level course what we are going through at the moment. Thank you very much.